fits everything. So what is cy?
Negative C1 sine t plus C2 cosine t plus 1.
To gas. All right. Plug that in. So x equals negative c1 sine t plus c2 cosine t plus 1 plus t. That's dy. That's dy, and then plus t is there from the relationship to begin with. And actually, I mean, you would put like terms together if there were any, but there aren't. I'm done. That's it. That's what x is.
That's nasty.
All right, second.
That's nasty.
Nasty? I mean, now think about it. When you heard me say systems of differential equations, you probably had in mind something this hard or harder than this. Now understanding this is not a very difficult example of this. This is number 3 from the exercises, by the way. All right, so they are going to go. They're going to have some second derivatives in there. So, but the basic idea doesn't change, right? What can they do? They can put a second order. They can put a d squared. All right. Well, if there's a dx and there's a d squared, actually take d on that side, so they'll cancel each other. I mean, you start to see the idea. It's not as simple as algebraic systems of equations where I just had to multiply by shit. Now I've got to operate with shit, right? I could still multiply by stuff if that's going to help me. But most of the time I'm going to involve operating with the d operator, the differential operator. Okay, I like it. Yes? Oh, you're good. I want to try to, we got the answer here. Let me put the answer down. Let me put the answer over here. Go away. Just to keep it. I want to show you what this would look like doing it the other way. That's a C2, by the way, poor little thing. Plus 1 plus t. That was a minus 1. Okay. All right, now, let's pretend like we didn't get this yet. And let's redo this and get x straight the way, same way we got y. So how do I kill x now? I'm sorry, how do I kill y now? What would I do to kill the y's? Yeah, take the first one, take his derivative, and that would be d squared x plus dy equals 1. Then what do I have to do with this guy to make sure that they actually cancel? Yeah, I've got to change the signs, right? So it'll be x minus dy equals t. Is everybody cool with that? So I did have to multiply by negative 1, so that multiplying by constants could still be a part of this. And then I get another little differential equation, d squared x plus x equals t plus 1. You can already see that happening, right? And again, it's the same idea. I'm going to have the same auxiliary. In fact, I forgot to do this, but can you guys see? Let me see if you guys get this. If you've taken linear, you're a little more used to this. And I know it's been a while since I said that, so I feel like I can say it without annoying you too much if you haven't taken it. What is operating on x completely? D squared plus 1. See how that's the auxiliary equation? Already? Right? I don't have to go through any m shit. Mm-hmm. You guys see that?
Yeah.
Just like over here, I went through the m shit, but I could have just said d squared plus 1, operating on y. Right? Mm-hmm. Okay? And so I get, of course, I'm going to get the same stuff I got over here. So far I got x equals C3, because I've already set C1 up. Can't assume it's the same. And it's going to be the same stuff, right? C3 cosine t plus C4 sine t. And hopefully you guys can see that if I went through the same process, I would get x for this guy would be for the same reasoning, right? This would be plus t plus 1. So this is not good enough because, where'd you go? I got C1, C2, C3, C4. That's no good. So how would I, now again, I know that we solved this. I just want to show you how it looks this other way. How would I go about equating, getting those constants to be based off of each other? Getting C3 in terms of C1 or C2, C4 in terms of C1 or C2. How would I start that off? What do you think? Do you guys see that if you do this kind of thing, you kill the x's and you get an answer, kill the y's and get an answer, you are going to end up with too many constants. Mm-hmm. So what is going to force those constants to show you their relationship? What am I going to do to force that out?
Plug it back in.
Plug it back in. Yeah. Plug it back into what's causing them to be related to each other, right? Now do you see how that would so suck if there were higher order derivatives? You'd have a lot of kind of stuff to kind of drill down, but still. Dx dt. So what's dx? C3 sine t, C4 cosine t, plus 1. There's dx. And I need dy. I already did dy somewhere, but you get negative C1 sine t plus C2 cosine t plus 1. And now you plug them back in. Let's see. So it doesn't really matter where you go. Let's see. You might as well go here. I'm going to take this stuff away. So if I plug it in here, dx, negative C3 sine t plus C4 cosine t plus 1 equals negative y, negative C1 cosine t plus C2 sine t plus t minus 1. That's what that one says, right? And this one says negative C1 sine t plus C2 cosine t plus 1 equals, oh, I'm sorry, did I put the plus t in? Yeah, this is negative y. Did I do that right? Negative y, negative, you guys got to stay on my back about this, all right. This should be negative y, right? So negative C1 cosine t minus C2 sine t minus t plus 1. Is that cool? Could be. Let's see. Shouldn't it be what now? And make sure you guys are. You can see why you don't want to do this way unless you really, really have to. Right? You know, the other way we're done by this time. So I got to show you how this looks. All right. So there's dx. Is that cool? Mm-hmm. There's negative y now done correctly. Negative, 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 plus. Change the signs of y. Plus t. That's nice. Those kill each other. So do you see how you already have something you can work with? Those kill each other, right? And those are equated already. So what must negative C3 be compared to negative C2? And they got to be equal. So C3 equals C2. And what's true about C4 and C1?
One's negative.
C4 is negative C1. Is that, so if I make C4 negative C1, if I make C4 negative C1, I get a negative C1 sine, and of course C2 equals C3, I get C2 cosine. That was fun. All right. Yeah, I always get a little cringy when I do that kind of thing because I always hate that method. And you can see why. But it should still work. It should still be you just crank through it. All right, let's try another one. Let's try one that's a little bit different. Yeah, here we go. So we got what they want from this here? Some of you guys are like, more than I ever wanted, Jeff. All right. So let's try this here. Yeah, let me just cut to the chase. Right. So this is something, you know, it wouldn't start like this necessarily, but it's been rewritten. It's been, the y is, it's not factored out really. You got to be careful. Remember earlier we had something like, what was it, d squared x plus x. Do you guys understand? This isn't really factoring an x out. It looks like it, so it's okay in your own brain to say I'm factoring an x out. Just don't let that out your mouth because you're not. This is the operator on the x to cause that to happen. That's why x has got to be, if you put x out here, don't make a damn bit of sense. It's like saying the square root of 9. What? No. So, what's your gut say as to what I can do from this point here? Remember, what are you trying to do? What are you always trying to do when you're doing elimination with any kind of systems of equations? You're trying to make
something out.
You pick a letter, you make the coefficients the same, but with different signs, so that when you add them together, they'll cancel. Right? That idea doesn't change. It's just how I get there is a little bit different. I'm going to operate on stuff now instead of multiply by stuff. So what really is almost the only way I want to do that with this, which letter can I kill easiest? Can I make that become this? No. Can I make that become this? Okay then. So which letter can I kill easier? The x. Because what do I multiply by? What do I operate with on this whole thing to make that become this?
Second of the derivative.
You can do it. What do you think?
D.
Oh, d plus 1.
D plus 1. Wouldn't d plus 1 times d minus 1 become d squared minus 1? Okay, all right. And see, that's the value of writing this in operational notation is I can then look at it like that. Even though I know it isn't true, but a differential operator is a linear operator, which allows us to look at it as if it was factoring and look at it as if I'm multiplying. Linear operators are awesome. As long as you remind yourself that's not what I'm really doing, but it looks like it, so what the shit. So if I take 1 and I operate on it with d plus 1, in fact I might as well operate on it with negative d plus 1, is that cool? D plus 1 to make it the same coefficient, negative to make it so it'll kill each other. Right? So I'm going to end up with negative d squared minus 1 x. What happens here? Minus, well, what am I doing? I'm being silly. This your job. Negative d minus 1, d squared minus 1 x. What happens here? Minus, yeah, let's just write it out. D squared plus 1, d plus 1, y equals, now what happens here? Let's write this out. Negative d plus 1 operating on 1. Okay, that definitely is kind of weird. But you just write it out and then work it out the next step. Let me stop here. How do you guys feel about what has just happened? Like some of you guys aren't speaking up, but you're like this. Keep going. All right, just had to remind myself it's this one I was operating on. All right. Real quick, on this side, what happens here? What's the derivative of 1?
0.
0. And now I got negative 1 times 1. Negative 1. Because this operator is a multiplication operator. That's nice. All right. And then here, when I add these together, oh, and then I'm going to add it to this. Did I already add these together? No, that was just making, all right, I'm just making the new thing. All right, got to keep myself together. All right, now I can add these things together. All right, you ready? I'll do the first part. These kill each other. And then I get d plus 1 y minus d squared plus 1 d plus 1 y. Right? Is that cool? Bam, bam. Is here. Yep, right here. So these killed each other. This plus this is here. And then I have 2 minus 1 is 1. And now I just need to clean that up a little bit. Yes, sir.
So how come you wrote the d squared plus 1 before the d plus 1 on the first 3 lines?
It doesn't matter.
Doesn't matter?
No.
Okay.
Again, differential operators are linear, so it doesn't matter if you operate with this one first or that one first. Is that cool? Yeah. All right. Yes.
But it does matter that y is
Yes, totally.
front.
I really want to make this make sense. When I have like this, d squared minus 1, we did one like this just earlier, right? And it was operating on x. I can factor this as d minus I, d plus I. Is that cool? Operating on x. Does it matter which way I write those? No. So it doesn't matter which way those operate on the x in the same manner. Okay, I like it. So just because we might not be very comfortable with this yet, let's kind of write this out in pieces just to really see what's going on. Does that sound all right? It's going to make this a little worse than it has to, but let's just do it once. So this would be dy plus y. Is that cool?
Yeah.
Okay. Over here, I'm going to get, I got to FOIL this out, right? D cubed plus d squared plus d plus 1. Is that cool? So we get dy plus y minus d cubed y minus d squared y minus dy minus y equals 1, because of minus.
Doesn't a dy cancel that one?
Yep.
The y cancel out?
So the dy cancels, the y cancel, so I'm left with negative d cubed y minus d squared y equals 1. Now again, I know there's a layer here that you have to understand. We're not actually factoring, we're not actually multiplying by these operators. But since it's a linear operator, it looks like that's what we're doing, and that's good enough to remember how to do it, right? Let's see. So what can I...
Take out
D squared y.
negative d cubed minus d squared.
Now, if I want to rewrite this thing, right? I'm at that level where I can rewrite this thing to really look at it more like I'm used to. Or maybe not. Maybe this is, yeah, how can you rewrite it? Take out the, what can you take out? You can take out a negative. Let's just multiply both sides by -1. Is that cool? I don't like that negative on that side with all those differential operators. So now I can do d squared times
D plus 1. Y. Negative 1.
equals -1. I like it. Let me see. It's a good place I could say that. Yeah. Watch this real quick. I want to make sure I got to the point where I could say this. Is everybody cool with this? It's not a bad way to do it for right now, because it's nice to kind of see exactly all the shit that happened. Can you guys see right here I could factor this? D plus 1, d squared plus 1, y. Oops, you can do better, Jeff. D plus 1, and then a y. Now here's where things get interesting. That means that would be 1 minus d squared plus 1. Wouldn't that be d plus 1 times negative d squared? Isn't that exactly, like I took a negative out, but then a d squared d plus 1? All right, so you can see that? Okay. So again, it looks like I'm factoring. Might as well stop saying it, because, I mean, it looks so much like I'm factoring, might as well just say I'm factoring. But not really. Now what do? This is going to act like my...
M squared times m plus 1.
So it'll be, yeah, m squared, m plus 1 equals 0. M equals 0, multiplicity 2, right? So that gives me what? This is my y.
plus C2x
C2x.
Good?
plus e to the negative x. C3 e to the negative x.
All right. Because this will be e to the 0. And then you can't have another e to the 0. You got to multiply by x. And then, of course, that's e to the negative x. I like it. And then I have to get this guy. Now, the weird part about this is you got these higher order derivatives going on, right? So, how do I say this? In fact, what saves your ass, and this is kind of like a neat side effect of this requirement. If I just look at this, what do I want yp to be? Just by looking at this. A. How do I know that can't be it? Yeah. So then I assume it's ax, but can it be ax? No. Ax squared, is that good?
Yeah.
Yes. And you see, it's kind of built in. The higher order derivatives couldn't let the y be a constant because it would have killed itself totally by this point. You guys see, if I let y be a constant, it would kill. So the nice thing is it's built in to the process to force you up a couple levels. Maybe some of you guys see what I'm saying. Maybe some of you guys are like, please make this better. All right, what the shit do I do now? I don't know what it is yet, so let's see. Y. So let's work with this guy, right? Y prime is, and this is d by dt, right? So it should really be t here. That's better. Yeah, it's real easy. I'm kind of happy to make mistakes like that right now, just to show you how easy it is to make that kind of mistake. I don't want to artificially be perfect. I make that kind of mistake all the time. Why? Because we normally are working with y as a function of x. But you got to be on yourself all the time like that. So y prime, 2at, y double prime, 2a, y triple prime, 0. So then you just get 2a equals -1, so a is 1/2. Okay. Are you guys appropriately tired by now?
I am.
Now, I want you to realize something. These problems can be long, but they aren't difficult. You got the little things you got to be careful about, like the thing with me putting an x. You got to remind yourself, no, it's a t. T is my independent variable in these, unless they say otherwise. So what I have really, that was yc, so what I really have here, let me just add it on here. I got -1/2 t squared. So that's y. Now, how can I get x? Yes?
Sorry, should the other x's in
Yes,
that y should
totally.
they should be t's? Okay.
Should be t's, thank you. There we go. Let's all help each other out. Otherwise, it gets really confusing because you have a whole other x idea in this problem. Holy shit. Now, what can I do from here? Yeah, I could. Totally. Which one of these would you rather use? I'm trying to figure out what x is.
The first one.
Yeah, why the first one?
Not two derivatives.
Because there's not as many derivatives of x that I have to undo. Does that make sense? I know what y is. I need to figure out what x is. So I want the one that has the least amount of shit happening to x. So that's the least amount of shit I got to undo. All right. Good, good, good. I'm trying to show you the examples that kind of help you figure out how to look at these things, how to attack these things. What can I get rid of here? This I have to get rid of all this, right? You guys got all that, hopefully. Everybody all right so far? Any questions? Again, some of you guys look pained. I'm sorry. But nobody's asking questions, so I'm going to continue. Of course, me right now, I'm saying that would have been great if I would have had time to do this ahead of time. But it's all live. Let's do it live. So I appreciate any help with mistakes. So if we look at the first one, d minus 1x plus, I got to know d squared y. So what's dy?
C2 plus negative
Yeah, C2 minus C3 e negative t
minus
minus t. And then what's d squared y?
C3 e to negative
Yeah, that's gone.
need to
Negative comes down, makes it C3 e negative t
minus one.
minus 1. That's beautiful. And of course, what is making me do that? Because the one I picked needs that. All right, so the one I picked has got d squared y plus y equals 1. So I got d minus 1x plus d squared y, c3 e negative t minus 1 plus y. So that's the d squared y. Plus c1 plus c2t,
Plus C3.
c3 e negative t minus 1/2 t squared equals 1. So there's d squared y. Yeah, Jeff, that's good. Underline with the same kind of underline. There's y. Wow. And there's equals 1. Yes, sir.
Is that second C3 e to negative t still need to be there, or can it be absorbed into the first?
Oh, totally. Now I can start doing stuff.
Oh, okay.
So that C3 e to the negative t was, the first one is from here, and the second one's from here, right? Why is that a, oh yeah, the second one's from here. There you go, Jeff. Good job. I was kind of hopeful they'd kill each other, but no. All right. So I get d minus 1x. So let's see what we got. We got plus 2c3 negative t. Nothing else happens, right? Plus c1 plus c2 t minus 1/2 t squared equals 2. And now I'm going to pull all this stuff over. And there's only one level of derivatives, so we only have to do one integration at the end here. Well, actually, what form is this going to be in? This is, this might be a good candidate for doing it that other way. Do you guys see what's going to happen here? I got dx minus x equals 2 minus 2c3 e negative t plus, gather plus, minus c1 minus c2t plus 1/2 t squared. Just moving all that stuff over, right? What form is that in? This isn't too bad.
The D first order.
Integrating factor.
Yeah, integrating factors in linear form. Can you guys see that? This would be dx dt minus function. So that's going to be p. X equals function of t. Function of what? Function of t. I like it. So that's the part that I think is the hardest part about this. You have something that feels a lot like just normal system of equation stuff. And then it immediately leads to you having to think back to chapter 2 or chapter 4, depending on what the hell level of shit it is. You know, and that's a little bit, that's like going from first to fourth gear, which you don't want to try to do, right? But you got to try to do it on these. But again, just to point out, we're already kind of like knee deep into this method, but you could have just tried to eliminate the other variable. Why would that have been really difficult, though? How do you kill the y? I'd have to multiply this by p plus 1 and this by d squared plus 1. It just, do you see what I mean? To make them match, you have to give them each other. Aw. Sorry. And again, if you can't see this, when you start to look at it as a dE, you can always bring back this notation, so it just kind of puts your brain more into where it needs to be. That you're not used to the differential operator notation, but you can see how it's helpful. But the minute you have to look at it as just a dE, maybe bring it back to that notation. Your brain kind of goes back in the right mode. So now, integrating factor, what's it going to be?
E to the negative t. Resist.
So you just get e to the
Negative t.
e to the negative t. So then this becomes d,
E to negative t.
yeah,
X.
e negative tx. I got to multiply by e negative t. So this becomes 2 e negative t minus 2c3 e negative 2t minus c1 e to the negative t minus c2 t e to the negative t plus 1/2 t squared e to the negative t. And do you see the beautiful thing ahead of you
Yep.
with this? Because now, of course, you've got to integrate both sides, right? what's underneath here? I'm going to pull over there, of course. dt. Here, I'll do half of it. I'll do this side.
No problem.
And now, of course, I mean, there you're going to have a couple of whats?
By parts.
By parts, yeah. Right. I really don't want to do that right now. 'Cause that's the level you guys should be able to handle that. But you notice it, and you actually go, oh, thank God, it's just that. Really, hopefully you guys understand.
Yeah.
That was like the first thing you learned in 280 was by parts, right? Oh, okay. It's been too long. All right. And then once you get that done, you divide by e negative t, or multiply by e to the t, and you'll have what x is with the correct constants, because we use substitution to get there. I like it. Okay, okay. All right. That's really all I wanted to say about 4.9. Travis, you got a question?
Yeah. When after you integrate all that stuff, would you get a plus C4?
Let's see. Yeah, let me think. All right. Yeah, actually, okay. Do you see how, all right, this is going to be a little bit weird. It's already weird. Do you see how everything up here is, involves derivatives in some way, right? I mean, this has got a piece that's -1, but it's kind of like whatever x is, it involves a derivative of x. I think, I can't remember exactly what to do about that. I think it's okay since it's all derivatives. The very first one we did, well, even that would be the same way. What do you think? I got to think about that. It's been a while since I did one like this. Integrate it to do the last step. I got to think about it. Because normally it would introduce another constant, but then that would take them apart from each other. All right, I got to think about it. That's a good point. I mean, that should bring up another c, which will kind of suck. We don't want that. Yeah, because nobody's... Yeah. Okay, yeah. I got to think about what would happen there. Any other questions about the idea behind how to do those? So again, if you did that one annihilator section, you're a little bit ahead of the game because you're a little more used to the operator stuff, but the operator stuff is not that hard to get down. It was actually the next level of that was a little bit harder to get down. I'm not going to get off my own back about that, but I'll figure that out. It's been too long. Okay, I want to do one other thing tonight. I want to give you, well, first off, I'm going to give you something to kind of like jolt your brain awake a bit with series stuff. This is you're never going to have to do anything related to this. It's just me just showing this to you, right? I don't know if you guys ever seen it before. A lot of the early history of working with derivatives actually came out of work that was done with infinite sums. No, that's not even the way it was first thought of. All right, so this is just me. I just want to show you something that I don't think you get to see very often. I mean, just look at the very top before you try to start looking at anything, right? There's no way in hell that that's obvious to begin with, that the sum of 1 over n squared equals pi squared over 6. And the first thing I would think, if that's the first time I ever saw that, I'd be like, where the shit did pi come from? But then when you start to realize how often that pi comes out of places that it seems like it should have no business Then you start to really appreciate pi. I mean, right now I don't know if you appreciate pi really. You're like, whoop-de-doo, you divide a circumference by the diameter, you make it bigger, make the diameter bigger, everything's bigger, so it's going to be the same stupid number, whatever the number is. But pi goes beyond, like E goes beyond some of the first ways you are introduced to E. Pi goes definitely beyond anything you would expect it to be doing. It's like, what the hell is it doing there? You don't have to look at this if you don't want to. I just wanted to kind of give it to you a little bit. This is nothing that I'm going to ask you about or anything. You guys understand? So I know some of you guys might be the type of students like, why the shit you give this to me? But I'm hoping most of you guys are like, oh, that's interesting. I might look at that. As you put it somewhere and forget about it. Okay. It's really got some cool shit to it. A lot of the early history of working with this stuff dealt with infinite sums. Taylor series didn't start with derivatives and they created it. They created the series and then they said, hey, that looks like it's an idea of a derivative. And that's how they kind of came up with some of the early ideas. It's neat. The next thing I want to give you, this is definitely something that's related to a lot of what we're going to be doing. Okay. And this is the one you definitely want to look at.
I'm a little confused because I thought 1 over n squared went to 0 because it didn't go up fast enough when you did like the harmonics.
Oh, the limit is 0, sure.
Yeah.
That can come on.
So one of the main things.
So
guys, let me ask you this:
and I'll send you whatever you need.
if the limit of a sequence is 0, does this bring back memories? If the limit of a sequence is 0, can you say anything about the series? What's the sum of 1 over n? The infinite sum of 1 over n. That's the harmonic series. I mean, not harmonic.
That's 0 because it goes to
No. Not the limit of 1 over n. The sum of 1 over n is n goes from 1 to 0 to infinity.
Like the second or third chapter in 280.
It's divergent.
Hence why I'm more.
You guys remember? I want you to realize that we're going to review a little bit more than we actually have to apply for this class. Okay? Did everybody hear what I just said? Because in general, you want to know a little bit more than you really have to know to do some problems. And if you don't understand why, then too bad. I'm going to make us do it anyway. So, like, if I say something like, do you guys remember the P test? I'm not talking about, well, you got some pills and okay. No, I'm not talking about that. I'm not talking about do you want a job, then go pee in the sky. No. The P test, 1 over n to the P. Right? If P is greater than P is greater than 1, the series will converge. Because 1 over n diverges. And of course, if it was to the negative power, then screw it. That flips it up, and it's going to diverge like crazy. So I don't know if you guys remember the P test. Because what I like to say when I teach series is 1 over n doesn't get out of its own way fast enough. What the shit do I mean by that? The most simple thing I start with when I very first start talking about series is 0.1 plus 0.01 plus 0.001 plus 0.0001. Right? I'm sure that somewhere along the line you've seen something like that. Just to make you believe, if I just say I add an infinite number of numbers and can the answer come out anything other than infinite, and most of the time people are like, no way in hell. What? Well, sure, if it gets out of its own way fast enough, and that one perfectly gets out of its own way. 0.1111111, right? So that becomes 1/9. Ooh, it's finite. Right? 1 over n, those terms don't get out of their way fast enough, so that's why it diverges. But 1 over n squared, they do. That one goes to 0 fast enough.
Or 1 over factorial will do it too.
Exactly.
Yeah,
the factorial, get out of here. That's an insane thing as far as growth. Okay.
An exponent.
So let me see. You want to look over this. Make sure you have not a grasp enough that you could pass a test where it was a bunch of ratio and root tests and shit, but that you remember it. The thing I love, do you guys remember geometric series?
This is one where it's like multiply by the same number over and over.
Yeah.
And the rule is like if it's less than 1 or 0 conversions.
How much I hate this.
Here, this is the last thing I'll talk about today. I'll let us out here a little early, but geometric series.
1/3, 1/9, 1/7.
Let's see. I don't know what do I want to start at? 1, sure. Right. So sum a n. I know it's normally c n. Who cares? R to the n. Oh, so I'm off already. Oh, there you go. N equals 1 to infinity. Is that cool? Yeah. This will converge if
Absolute value bars. That's the one.
and
Can't be 0, right? Can't be 0. Can't be 0.
It's less than 1.
yeah. Well, if R is 0, then this is the sum of zeros forever. So that like converges trivially, right? Trivial convergence. If you have 0 forever. Okay, I'm not going to waste my time. Let's find out 0. The one connection I want to make that I think some people don't make for their students is the one I try to make for you where it says the ratio test. So if I have a series, A1, A2, blah, blah, blah. You remember the ratio test was looking at the limit as n goes to infinity of an plus 1 gather over an. And that had to be something that where L was less than 1. But what is, like up here, what is this term divided by that term? Actually, I guess I should make it, let's do it like this so it's a little bit easier to look at. What is this term divided by that term? R. Right? So eventually, do you guys remember how it doesn't matter what happens in the first 18 billion to the 18 billionth power numbers. All that matters is what happens starting somewhere and forever after that. So if somewhere this becomes less than 1, which means that would be the limit, right? So it could be up to the trillion to the trillion to the trillion to the trillion to the trillionth place in this sequence could be greater than 1, and then forever after that it's less than 1, this ratio. That is related to this, because that's what the hell this would act like. That's the multiplier between two sequence elements. That's a connection I don't think a lot of people make. So always remember this. Remember the hard part about this, depending on which teacher you had? If you had me, you had to remember this shit. How to interpret the results. If you had somebody else, they might have just given this to you, and then I'm like, well, what do they learn? But the way I remember this is it's geometric. Less than 1 means convergent, because that's what geometric. Less than 1 means convergent. All right, that's enough of that. I'm just trying to dredge up some memories right now of some of this stuff, just to get that stuff back in your brain. What we're going to be doing is, did I do that? No. Yes, I did. I already told you that was the last thing I was going to do. I'm going to stick to it. Notice on the back, we'll do this thing first thing next time. Verify that that series solves that DE. Right? So we're going to have to talk about that. The hard part about this section for people is how to combine two series if things are out of whack between them. So if you have a series that starts at 1 and another one starts at 2, how do you handle that? If you have one where the insides aren't like terms, like you have a sum x to the n plus a sum x to the n plus 1, well, shit, right? One thing would involve, what I call shucking. You shuck off the first term, and now these match. The other one involves a translation to make the powers match. So, well, that's the hardest part. So I want to focus on that by itself before we even get into full how to find the series solutions to DEs. All right. Oh, okay. All right, that's enough for today, I believe. Anybody not get their test back? Oh. All right. Huh? Yeah.
No, that's not bad.
Man, this is all out of order.
The series is nothing more than a summation.
Oh yeah, man, you need your certificate. You're here.
Couldn't tell you.
Do I pass you by?
Patterns is not mine.
That's what's coming in this class. Oh, do you recognize doing this in homework? Nope.
Jose,
I
I
recognize
got
doing
this thing
something.
with Lynn.
I never do. Every time it's math, it's
Oh,
like doing the
right
new
there. Let me know that grade sheet makes
That's why I'm
sense.
good at work and I'm able to learn new shit because I don't recognize jack shit after. I should say there's like the ROs.
I'm not to the point.